Hello, everyone. We are team turbotrackers. We are proud present our final project. Our project is for developing an autonomous driving system for F1 tanks that can reliably follow line markings and avoid obstacles in real time on a circular track. And that's our motto, autonomous driving has the potential to revolutionize transportation by making it safer and more efficient. However, achieving rapid line following and obstacle avoidance in real time remains a significant challenge, especially on circular tracks where environmental noise and decision-making complex come into play. Next, the goal of our project is to create a system capable of accurately following line markings and avoiding obstacles in real time on a circular track. To achieve this, the system must ensure safe and efficient driving while addressing challenges like sensor noise, real-time decision making, and environmental uncertainty. Our approach involves four main components. The first is land detection and finding the future points, pursuit control, and obstacle avoidance. And in the line detection module, we apply a color picker to determine the HSL range that best captures the line markings while filtering out the environmental noise.
So finding the future point is the most important part for our algorithm. After obtaining the polynomial of the road through the previous step of land detection, we draw the predicted road in the bird view picture, which is the yellow line. We then plot the position of the car, and using the car as the center, we draw a circle with the radius equal to the lookout distance. The intersection point between this circle and the yellow line is the future point we need to find. Here, the lookout distance is our hyperparameter. After several adjustments, we have chosen the size of that much, and then we convert the future point into a coordinate system with the car as the origin to calculate of a relative position and the relative angle between the car and the future point. After obtaining the relative angle, we use the pure pursuit method to calculate the steering angle required for the car to reach the future point. Here, L refers to the wheelbase distance, alpha refers to the angle between the future point and the car, and LD refers to the lookout distance. Using this formula, we can obtain the car's steering angle delta. Additionally, we introduced a new hyperparameter K, which is used to adjust the car's steering angle. This is because there is a certain discrepancy between the real-world situation and the theoretical calculation. So by adjusting the value of K, we can ensure that the car can perfectly circle around. Ultimately, we choose 0.6.
In the obstacle avoidance, we use the leader. We handle the data point within -10 and 10 degrees ahead. We have found that 0.8 meter, which is safe enough for stopping. Next, as you can see in the table, we test three different velocities. For velocities of 0.8 meters per second, the car cannot move as expected. We think it is because the motor at 1 meter per second, the cars complete the loops in 14.4 seconds. At the velocity of 1.2 meters, the completion time is 13.14 seconds. We tested the system's performance under the different obstacle weights, and we found that the obstacle weights won't affect the avoidance functionality. Next slide. Here is the result for our F1 tens completing a loop. Our car can stop before the obstacle. Once the obstacle is removed, our car can continue moving and follow the track.